So now we're on to sort of the next step in this whole quantum mechanical thing. So now we're going to start officially looking closer at quantum numbers. Right? So I guess what I'm going to do is I'm going to actually do a slightly separate little segment that's going to cover particle in the box right out of your first year textbook. So what I'll do then is I'll go over a few key elements of quantum theory, but the most important part for that one is to show you how a quantum number comes about. So I'll save that for our next segment. This one I'm just going to kind of go over quantum numbers itself. So I will present that with the idea that the infamous or famous Schrodinger equation looks like this. So the idea is this. You have a wave function. It's just a math function. And one way to look at it is, if I said in math class f of x, that's all that this means. You have a mathematical function of some sort. But it has to satisfy an interesting thing. Anything that has a little hat on it, like accent circonflexe, I didn't say that right, but this is the Hamiltonian operator. That's what this hat means, operator. This basically performs a mathematical operation on your math function. And it has to give you back the same function intact, but with something out in front, which essentially is the allowable answer to the operator question. And the Hamiltonian says, what is your total energy? It's almost like it's asking the mathematical oracle, if you will. Why do I call it the oracle? Because the wave function is supposed to include all the possible information that is related to observable outcomes that you could ever see. So information of your system modeled with this math function contains all the observable outcome-based information. So in other words, anytime you test this through experiment, this does include all the possible answers for what you could ever observe. So that's why you're asking this almost like it's the oracle holding all the information of your system, if you model it right. And this one is asking a specific question: what is your total energy? And this spits out in front of your wave function. So this is the Schrodinger equation. And it's a big deal because there are many other types of questions you could ask it. For instance, you could say, what is your position in the x-axis? What is your momentum, right? These are different things. Different mathematical operators are going to ask this question. But this is one of the most important ones because energy, like all things, is a big deal in physics. So when it comes to a box or a cage, such as, here is a system with a positive nucleus. And remember how I said last time, the easiest one is to start as the hydrogen, or any one electron system or atom. One electron system only, okay? So you could just say, okay, what we're gonna do is we're gonna throw in one electron and we're gonna watch what happens. And just for example, the 1s orbital, if it's that energy, poof, it's like throwing one electron and, boom, you have this orbital. The electron becomes your orbital. That's what it looks like when we're not looking directly at it. It gets spread out, okay? Well, it turns out that when you're looking at the nature of this particular cage or boundary condition on one electron, the trapment of it, what this process ends up spitting out as long as you go, and you'll see how that arises. The first one is the principal quantum number. And when you go through it and see, the math is going to spit out, in order for you to ask this question and perform the operation you're supposed to successfully arrive at the answer, what is forced to come out, and you'll see how these quantum numbers get naturally born, certain constraints of the system say, to make sense of this, you need 3 quantum numbers. The first one is n. We're not going to go over exactly how it did it, but there's other books that you could see it, but you have to trust me on that. So the principal quantum number is what that one's called. And a lot of books will say things like, it partially indexes the, I just caught myself. So many textbooks and things where this is, people will say, oh yeah, well the high school book or this one, no, they made it clear. And I said, what do you mean they made it clear about a one electron system versus the others? So I go back, and what I see is not a big figure on the side. I see a little tiny piece of a sentence, almost like a lawyer's stamp on something saying, no, 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 we told you. So before I go back to this principal point, what did I say right here? Any one electron system. So you know what I'm going to do? I'm going to write down right now, before I screw this up, an important diagram, figure. And it's going to look, I'll start it. For a hydrogen atom, and those of you who have had electron configuration, you're already going to know this, right? This is increasing energy. These are the allowable energy states that the math is going to spit out. And then you have a 3s, 1, 2, 3, 3p, 1, 2, 3, 4, 5. That's the 3d set. Now notice very carefully, 1 electron atoms only. Okay? So you see in a tiny little corner somewhere in the book, this little diagram. Only when you have one electron systems, and that's why a lot of books are gonna call this hydrogen orbitals and energy, like ranking. If this only applies to one electron systems, notice would you notice any energy difference between a 2s orbital or one of the 3 2p orbitals? And the answer is no. This is called degenerate. So the only thing in a one electron only system that tells you the difference in energy is this principal quantum number n. So if one electron, it gives the energy. If more than one electron, it assists, if you will, in the energy. But it doesn't completely give you it. So this picture, and you need to put this in your head, one electron systems only, hydrogen orbital systems only. They're all degenerate the same. Principal quantum number n does give you that. That's why Bohr, in his model, all he needed was one number that he called planetary orbital 1, 2, 3, 4. That's all he needed. Okay, but if you have more than one electron, this is what you're going to be more familiar with. And if you pick up any periodic table and you start at, imagine all of the boxes in the periodic table had no atomic symbol written in it. Let's just say they were like empty mailboxes to start with. You're going to quickly realize that the very first box that H happens to sit in, and then the next one, helium, ends up being the 1s orbital. This is energy. The next one in line, after helium, you look at the boxes of lithium, beryllium. Those two boxes essentially represent the empty mailbox of the 2s orbital, if you will. So far, so good. But then you move on to the next one would be boron, carbon, nitrogen, oxygen, fluorine, neon. Well, look at this. 1, 2, 3. 2p. The 3, and each one can hold 2 electrons, so that's the 6 in the p block. But notice how it's slightly higher in energy. And this is going to be called the relative scale for energy, and still use the 3 quantum numbers, which give you the principal, this one, plus the ML number will give you how many of these you get. We'll cover that in a minute. Still use, this is a huge assumption, and we are going to cover that. After the 2p block, you come back to the s block, sodium and magnesium, so the 3 s's here. And then you move on 1, 2, 3, which is the 3p block. And then after the 3p, you come back to the 4s. After the 4s, you start filling in 1, 2, 3, 4, 5, the 3d block. Slightly higher in energy than the 4s. Folks, this one, and I'll draw a really nice version of the relative, not exact, because the approximations they made to keep these quantum numbers, to keep the idea of 1s, 2s, 2p, and all. As soon as you have more than one electron in the system, this is the relative filling in order of the allowable energy states. And keeping the quantum numbers that came out of the exact solutions for hydrogen 1 electron systems only, we're keeping that. But this degenerate scale no longer exists. You get this relative one. And the periodic table, as you fill it in box for box, follows this progression, okay? So that is useful for us to know. And we start off with the principal one. So in other words, even in a multi-electron system, it ends up being this first number. And it helps arrange some of the energy scaling. The L number also does play a part in it, right? Because you can see here, a 4s, even though it has a higher principal quantum number, is a little lower in energy than a 3d. So just because the principal number is higher than this one, it turns out that the 3d one is slightly higher in energy than this one. So that's why we say it assists. So next up, you have what they're going to call, I think our book at the moment calls it angular momentum quantum number. Others call it azimuthal? The azimuthal quantum number. Blah, blah, blah. Well, look, the interesting thing about this one is when you're solving the Schrodinger equation for hydrogen atoms, even for a hydrogen atom where they get exact solutions, and when they make approximations for many electron atoms, they get similar quantum numbers. But the point is, there's something about this L number that is related to what had to be true about the mathematical function they were modeling. So the boundary conditions of the spherical geometry, etc., the energy minimization, you name it, this gives information about the shape of the electron density and hence the actual orbital that the electron becomes itself. So there is aspects about the shape. And L is very much linked to, in quantum mechanical number says you have to start at 0 and then you can only go up by integer numbers. So you can start at 0 and then you can go to 1, 2, 3 and so forth. So what happens here is, for this one, the geometry or shape related to the quantum number being 0 is spherical. So these are the classic, your electron density, the orbital the electron becomes has to be spherical in shape, like a basketball. Okay? So we almost have to trust that a bit, but the math dictates this has to be the case. If, however, you are using a different next in line allowable quantum number for L, the shape is going to switch to a p orbital type of shape. So this is an s orbital type of shape, this is p. This one comes up to d orbitals, and you have to now look in your book because some of the d orbitals kind of look like a clover leaf. One of them looks like a donut with a p in the middle. These are the types of shape related to d, and I might as well do it at the same time. The ML number, which is called often the magnetic quantum number, okay, that one is very closely related. The mathematical solution forced these two numbers almost to come into being at the same time. The L1 had a lot to do with the shape, right? But the ML had to take on numbers from the negative value of L, counting by integer numbers, all the way up to the positive value of L. So if we did it for S, if the L is 0, you start at -0, and guess what? ML equals one number 0 for an S orbital. Okay, so what that says is, when you talk about S orbitals, they only ever come as one orbital. That's what that is. So the ML number actually gives you an indication of how many of the L-shaped orbitals you have for the principal quantum number you're working with. So an L, going back here, takes on restrictions that whatever your principal quantum number n was, the L can take on values starting from the value of n up to n minus 1. So in other words, this is one rule as an example. So to cover up that one first, if n equaled 1, L can take on values starting at 0 up to n minus 1. So if somebody says n is equal to 1, then L is allowed to take on its first value of 0 up to n minus 1 value. So it can count up, and if n is 1, you're subtracting 1, then therefore if n is 1, the only allowable values of L is 0. And 0, when you look at the L number, that tells you the shape of the orbital and talk about s orbitals. Okay? And ML over here can take on values of negative L up to positive L. So there's no surprise, the ML number equals 0 for that. So what if we move on to n equals 2? Okay? We've set the principal quantum number. Now L is allowed to take on values starting at 0. So L can start at 0, and it can go up by 1 until it hits n minus 1. So it's allowed to go up to n minus 1. It can only go up to 1. So it can't have any. These are the numbers you can have. If somebody says n equals 2, that's the only information you know in the atomic structure world, then the allowable L values that this can take on. So what this means is, when n is 2, I'm allowed to have a 2s, and because L is equal to 1, that's a p, and the principal goes with it, so I can have a 2p. So the two types of orbitals and their shapes I'm allowed to have when n equals 2 are these. But now you're going to say, if I was talking about a 2s orbital, bing, bing, because L equaled 0, then ML can take on values of negative L all the way up to positive L. Because it's 0, ML is just going to be 0, which means there's only one S-type orbital, one 2s orbital. Complete the analysis on this. Because it's a p, and because L was 1, then what that means is the ML can take on values of negative L up to positive L, counting by integer numbers. So if I start at negative L, then my ML can take on negative L, negative 1, go up by 1, you're at 0, go up by another, you're at positive 1, which is the positive value of L. So guess what? Two P's are 1, 2, 3 of them. That's what that means. We'll do one more. What if n equaled 3? What are all the possible orbitals that can exist if somebody simply told you n equals 3? Okay, the possibilities are L can take on values starting at 0, counting up by integer numbers, until you hit the value of n minus 1. So 3 minus 1 is 2, so the L can be this. If it's a 0, it would be a 3s orbital, because the 0L means s. The principal number goes here. If you're talking about L equals 1, we already know that you're talking about 3p type of orbital. The ML number takes on negative L to positive L, so it goes negative 1, 0, plus 1. So that means you're going to have 3p orbitals. If I was talking about a 3n and L equals 2, that means d orbital. So now you're going to have a 3d orbital type of shape. How many of them can there get? Well, ML takes on the negative value of L, which is negative 2. Then it goes negative 1, 0, plus 1, plus 2. 5. So 3D comes in 1, 2, 3, 4, 5 different individual orbitals, each with their own shape. So this is the quantum numbers, the 3 main quantum numbers so far, and what's left over is one last one, which is the spin, okay? The spin. So for that, if you're talking about an electron, it's allowed to have either minus a half is their number or plus a half. So what that means is the spin it's allowed to have is either minus a half or plus half. There's 2 spin states. The other thing I want to point out now before closing this would be going back to energy spacing. So remember that diagram that said, for instance, if we're talking about the 3 2p orbitals, we knew that the ML numbers, for instance, would be minus 1, 0, and plus 1. Notice how they're degenerate. The reason why it's called the magnetic, the ML numbers, magnetic, guess what's going to happen if you took this? Let's say you had an atom that had one electron in each of the three orbitals. So these three p orbitals did exist, but they're at the same energy level. You know what's going to happen as soon as you put, and I'll draw this bigger, you got an electron in each of the two p's, the minus. So the ML numbers, which indicated there was three p orbitals, there's three of them. Now let's say you had an atom that had an electron in each of them. Just focus on these. Guess what happens if you were to take this and put it inside or next to a very strong magnetic field where the North Pole was here and the South was here? Well, now each of these orbitals, and each of these orbitals is 90 degrees to each other. So if I had this, X, Y, and Z, one p orbital is that way, one is this way, and the other is 90 degrees that way. And the thing about these orbitals is one lobe has a positive phase and the other has a negative phase. So take a wild guess what's going to happen to the energies of each of these three different orbitals when you stick it inside a magnetic field that has a direction of north and south. As soon as you do that, so if you put this into a magnetic field, you're going to get 1, 2, 3. Now, I don't know which one in this case is going to be which, but I know this. Each of these three orbitals will be at a different energy state. An experiment can now measure the differences between here and here, here and here, and here and here. That's why it's called a magnetic quantum number. When you're not in a magnetic field, the three p orbitals are the same in energy. Take that atom, stick it in a magnetic field, they differentiate in the energy because of the spatial relationship of their positive, negative phases, etc., with the magnetic field. So I think that concludes the 4 quantum numbers as sort of a quick overview of what they are and the rules of how they work.